So direct proof is one way that we can justify an assertion that we've made, but remember that assertion has to be a conditional statement. So are there other ways we can justify things? Specifically, what if we want to assert something that is not a conditional statement? Because if we assert something that is not a conditional statement, you can't even attempt direct proof. There's no hypothesis to assume, there's no conclusion to work towards. But there is another rule of inference that we can use called indirect proof. Here it is as a rule of inference. We can make a two-column proof and it's really quite short. Well, first we would state the given. The negation of P implies contradiction. In line 2, we can introduce a tautology. You know what's a tautology? Not a contradiction. Remember, contradictions are always false, so their negation would always be true. This is a tautology. But now, from the given, negation P implies contradiction, the tautological not a contradiction, if I apply modus tollens, with a hidden use of double negation, since I have the negation of the conclusion, I get out the negation of the hypothesis, so that's just P. So we've concluded our proof of this rule of inference. This is known as indirect proof. So if you want to derive the statement P, what you can do is you could assert the statement, the negation of P implies contradiction. Then you could do a direct proof of this by assuming negation P and working towards some sort of contradiction. That would complete a direct proof of your assertion that negation P implies contradiction. Now that you've asserted and justified that the negation of P implies a contradiction, you can use this rule of inference to conclude P. But there's a shorter way to do this. Notice all we really did was assumed negation P, derived contradiction, and then allowably concluded P. So assert the statement that you want, P. Assume its negation. Whatever the assertion was, this doesn't just have to be a literal, it can be any compound statement. Assume exactly its negation as an assumption for an indirect proof, and we abbreviate that as assumption for indirect proof like this. Now what you need to do is derive any contradiction you can. Contradictions almost always look like Q and not Q, a statement and its negation. By the law of contradiction, this cannot possibly be true. You cannot have a statement and its negation both be true at the same time. So this is a contradiction. So from our assumption of negation P, we derived some sort of contradiction. Therefore, this is what we've implicitly shown, meaning through this rule of inference, P must be true. We shortcut that by simply saying assertion P. Move to a subnumber. Assume the negation of what you just asserted and work towards a contradiction, and then you're basically done with the justification. Now we're going to see several examples of this style in action. So here's the first one. Well, we start off by simply declaring the givens. Okay, here they are, 1, 2, 3, 1, 2, 3. 3 givens. Now we know we were trying to get not P. I don't necessarily see how we can get out of that from what we have here, so I simply assert it. But not P is not a conditional statement. There's no hypothesis or conclusion, which means that direct proof is not going to be an option. I have to, however, move to a subnumbering system. So what we're going to do, since I claimed not P, I assume exactly the opposite as part of an indirect proof. Now I can't refer to line 4, but I can refer to lines 1, 2, and 3, and I'm trying to generate some sort of contradiction. As soon as I make a contradiction appear, I have finished my justification of this assertion, and once this assertion is justified, the proof overall is done. But now we have P to work with. There are a few things we can do. For example, I can perform resolution with lines 2 and 4.1 to extract, since I don't have not P, I must have had not Q. I could have also done modus ponens with line 4.1 and 1 to extract Q or not R. Both of these could have come in either order. But notice now I have not Q, and I also have Q or not R. And now what can I do? Well, we can take the not Q and Q or not R and do resolution. Okay, if I don't have this Q, then I must have had the other side not R. But I can also take this not R, feed it through modus ponens into this line and get out not P. Okay, so what next? Well, observe that in line 4.1, we assumed P. We were also able to derive not P. which means I can conjoin them and get P and not P. But this is exactly a contradiction, something and its negation. So from our assumption of P, we were able to get to a contradiction. So you box that off and say the assertion is now proved. We finished our indirect proof. Since this line is justified, the proof overall is complete. Let's look at another example. So here's the rule of inference we want to prove. So how are we going to start? Well, we start with our givens and then we can state our desired assertion. There are other ways we could proceed from the first 3 lines, but let's just go with this. We've asserted something that's not a conditional statement, so direct proof is not an option. We have to move to line 4.1, where we are going to do the only other style that we can possibly try, an indirect proof. Having asserted S, we assume exactly its negation. With this not S, there are a few things we can do. For example, I can do modus tollens to get out the negation of this hypothesis. So there's line 4.2. Okay. I can also rely on properties of conditional statements. The negation of a conditional statement is logically equivalent to a true hypothesis and false conclusion. This should be referring to line 4.2. I think it simply got caught off. Apologies for that. Now that I have a conjunction, I can specialize it. I get this and that by specializing line 4.3. Okay, what does this R and this not P get me? Well, remember, we assumed not S, and we're trying to find a contradiction, any contradiction at all. Now, since we do not have P, I can do modus tollens and say I do not have Q and R. Once I have a negation of a conjunction, I can apply De Morgan's law and say, well, either not Q or not R. So try to ask with the stuff we just generated, how can I combine it with some of the things we have to get something useful? Well, one thing we can do is we can take this R and this disjunction and resolve it. Okay, either not Q or not R. Well, we have R, so we must have had not Q. But now we've got not Q, and one of our givens was Q. So I can conjoin those and say both Q and not Q. So having assumed the negation of our assertion, we were able to derive a transparent contradiction. So that whole work can now be boxed off, and now the assertion is no longer an assertion. We've completed justification. With this justified, the proof is complete. As before, there are alternate proofs. Okay, so if you had another method in mind, it doesn't mean it's wrong. Let's work through one more example of an indirect proof. Well, it's going to start much like the others have. Okay, we state our givens, and then we see our desired conclusion, which we put in as an assertion. This is always a totally legitimate way to start a 2-column proof of a rule of inference. State your givens, assert your desired conclusion. Depending on what sort of statement you asserted, different proof styles might be suggested. Did we assert a conditional statement? Doesn't look like it. So direct proof is not an option, so we're going to try indirect proof. How does an indirect proof start? All right, we asserted a statement, but it was a compound statement. So we have to assume the negation of that whole thing. A common error would be to just stick a negation in front of here and think it was not Q or R. No, it's the negation of the entire assertion. Well, as soon as I have a negated disjunction, De Morgan's law seems reasonable. Now that I have a conjunction, specialization seems pretty transparent. Just pull out each of the individual pieces. Now we've got some new pieces to play with. Not Q and not R. Refer back to your givens and ask, if I have a not Q and I have a not R, which of these can be used? Well, since I have not Q, that's the negation of the conclusion of this statement, so I can feed modus tollens the not Q in this conditional statement and get out the not P. There it is in line 4.5. Now that I have a not P, I can resolve the given in line 1, either P or A, but not P, so I must have had A. Now remember, the style of proof we're going for is indirect, so having made this assumption, I want to generate a contradiction of some kind. Also ask if there are any givens that you have not used yet. So indeed, we have not used the given in line 3. If I apply De Morgan's law to line 3, I end up with not A or R. I can then resolve this right here to extract the R, but I also already had a negation of R up here in line 4.4, so if I can join those, I get R and not R. So having made an assumption which was the negation of our assertion, I was able to work towards a transparent contradiction. That concludes an indirect proof. So the assertion is now justified. Since that was our original desired conclusion, the proof of this is done. And again, this is not the only proof you could have come up with. With direct proofs alone, there are lots of variations that students tend to find. Indirect proofs have even more in my experience. There tend to be many more options because the contradiction you're trying to generate is not specific. Remember, in direct proof, you assume the hypothesis, you work towards the conclusion, both of which are part of the statement that you asserted, so form can be a little more restricted. Indirect proof, you assume something, and then you simply need to construct any contradiction at all. It does not matter which one. So they're much more open-ended. It can be a little unclear what contradiction you're trying to get, which means different people may find different ways of completing the proof, which is fine. There's usually lots of options. If you and your study partners come up with different proofs, do not assume that one of you is wrong. Check each other's work, and maybe you were both right.